So yeah, today I'm going to talk about EXPLORA. That is a joint work between ourselves, me, Claudio, and Jorg from India, and folks in Northeastern that started basically with a visit I did last year. And this is a work on AI explainability targeted to the Open Run. So to delve directly into the perfect. Was just not just working. That's good. So exactly, to come back, sorry for the interruption. So basically, explainability is not something new. DARPA has already introduced this back in 2016-17. And also at that time, there were already several works dealing with tools and techniques to provide explainability basically on ML AI algorithms that were dealing basically with computer vision and natural language processing. So this is really not something new. And at the end of the day, what this aims to is basically to break a little bit the today's chain, where you basically develop a model, you train it, you deploy it. At the end of the day, often you really don't understand why some decisions have been taken or why some predictions have been made. And explainability basically aims to break this issue by introducing techniques that allow you to understand why certain decisions were taken, even to understand why certain prediction errors were made. For example, we have a recent work that builds a tools on time series forecasting, and there we basically are able to pinpoint why some errors are due, for example, to hyperparameter mistakenly configured versus prediction errors that are due basically to errors that, because of the data, is inherently hard to predict. But that's not really the topic of today. So coming back to today's topic, this is about deep reinforcement learning. And basically with these agents, we take actions. We want to understand why they take certain action and which is the effect on the network itself. So to set the stage forward, I want you to first understand which is the agent that we are dealing with. So this agent basically is have been developed by the folks on Northeastern a couple of years ago, and basically takes very simple decision. It decides how many frequency resources it assigns for each slice. Each slice basically it's like a share of the network and also the scheduling policies. So basically it takes 2 actions at a time. And these slices basically are 3. And when you read EMBB, basically think about bandwidth intensive applications. When you read EMTC, read about machine type communication, so a lot of packets being exchanged. And when you read URLC, basically think about latency sensitive applications. So this agent basically what it does is that assigns resource, basically preferred resource allocation simultaneously on the 3 slices. And basically to do this, it analyzes and reads the environment that basically are user KPI and the past physical resource block allocation. And next, basically solves, try to take actions that provide a reward, and the reward basically is defined with a very simple function that is in the form AX plus BY minus CZ, where basically for the slice EMB tries to maximize throughput, for the slice EMTC tries to maximize the number of packets being transmitted, and for the slice of URLC tries to minimize the buffer occupancy as a proxy for latency. I want you to keep this in mind because at later stage will become very, very useful. So going further, I want you to point out few key unique properties of deep reinforcement learning. And this is basically important to set the stage how we develop our EXPLORA framework. So here we want to learn actions, and this is a finite, maybe large set, but is finite. Whereas, for example, if we think about traffic forecasting, when you have basically a sequence of past value to predict the future values, prediction usually are real values. So that's something slightly different. Possibly it's inhomogeneous data because, as we've seen, KPIs are very different. This is the input of your model and are very different from the output of your model. And if we go back for the time series forecasting, well, input and outputs basically are the same quantities. So those are very different things. But if we put this in analogy to computer vision, at the end of the day, imagine a classification task, and you want to classify images, for example, with given labels. So labels also are a finite set. And at that stage of thinking, I said, okay, well, then maybe we can use those tools that have already been developed for the computer vision and natural language approaches area. And then I was starting to think, okay, how can we actually explain this? And there are several techniques already there. So one, for example, is you have a very complex model. What if you try to simplify it using a surrogate model that is already self-interpretable, like, for example, decision trees or ensemble decision trees like XGBoost? And we did that. I will tell you later how. And also, at that point, the line of thinking was a little bit, okay, if I can compare with well-known techniques, will be the semantic of the explanation similar? And that was an interesting question. And I will tell you later why, at the end of the day, was really not applicable. I discarded at this point, like other techniques like teacher-student methods, because at the end, with a teacher-student method, what you want to do is to have like a student agent that tries to take decisions, and it might make mistakes. And basically, there's another network, the teacher network, that that agent basically it's like if guides to the right way the student agent. But this requires that basically you define very well your teacher, and this in an environment like the run, it's very hard because you end up having too many rules that have to be set. So basically, I start developing what I was mentioning before, like very well-known techniques. SHAP is one, and decision trees. And let's start looking a little bit at decision trees. So we have this agent, and basically you have your input. So if you want to understand why a certain action is being taken, what you want to do is basically to understand which input have been generated a certain action, right? But unfortunately, inputs depend very much on the actual scenario, right? Here we have a 5G network with multiple users. So actually, it's very hard to cast a decision tree for all possible combinations, and you have to develop many, and that's really not scalable as a technique. So what about if you just basically use this surrogate model on the agent? At that point, what happens is that basically you end up understanding which is the contribution after the autoencoder block. And that's basically latent representation of the stage, which allows you to create a very neat decision tree. We did that, and unfortunately, what turned out is that these trees become very huge. You can do pruning, but that's complex. You lose a little bit, and also the accuracy was not that good. So we end up not doing that. And also later we try SHAP. SHAP is an extremely well-known technique. Basically comes from game theory, and basically provides feature relevance according to Shapley values that exactly are a form of game theory. And here we encounter a problem first, because there was some code already available, but that was for a very old TensorFlow version. So we had to hack in and to understand how to do that. It was not so easy, but at the end we managed to do it. And we applied. We ran several experiments on Colosseum. So if you were asking from yesterday artifact talk, that's our paper that was run on Colosseum. And we did several experiments, and turned out that actually you can find some form of interpretation where basically the Shapley values, they will give you relevance. So low relevance is basically denoted in blue. High relevance is denoted in red here. On the bottom of the plot, you basically see the values in output of the autoencoder that have been fed to the DRL agent. And later, you see on the bottom, on the top part of the plot, the action that was actually taken, split between physical resource block and scheduling policy that was chosen. So here, and we find this consistently to the experiments, we were actually able to pinpoint that whenever we were able to get like a low relevance from SHAP, that was an indication that something was changing in the network. So nice, but unfortunately, this type of explanation, they don't tell us anything about any network meaning. So you don't know if the agent was taking this action to improve throughput, to reduce buffer size, and to us was a little bit intractable to use. Further, this is also very costly. So we were running basically this SHAP for a number of experiments and on several GPUs. And here I just show a couple of results where on the x-axis basically read number of users in the system. And when you get 4 users, this is already scaling to 26-hour computing, which is very, very hard to tackle. We also did test with a higher number of users. That was confirmed. Then, basically, at this point, we were to a point where we had like a number of challenges we've been tackling. We can summarize them as like autoencoders were basically breaking a direct input to output connection. So it was not really possible to understand why a certain action was taken. The challenge too was that given that this agent takes into account past physical resource block allocation, then basically we end up having a process that has memory into it. So models like casual learning were not really helpful here because we could not understand which is the main effect cause in the system. And also where actions, basically we term these as multimodal actions, where basically a single action was having an effect on several parameters in the network, then it's hard to understand which is the single effect of each mode of the action. So basically, we turn to a point where we were thinking that this really needs a rethinking if we want to create meaningful explanations. So we propose EXPLORA, that is a framework that basically does 2 things. One is that explain the actual agent behavior. And the second point is that using this explanation can also help improving the decisions and therefore the overall network performance. To do this, we use attributed graph. Why? Attributed graph are a popular technique, so nothing new here, but the way we use it is solving all the challenges and going through this. So as you can see, basically in the environment, we generate a state that represents how the network looks like now. The DRL agent framework basically reads the state, takes an action. And what we do here is that we record this action as a node of the graph. And then this action is actually enforced, so creates an effect on the network that is basically that materialized as the next step, right? So in the next step, the next state will actually record the effect of the action. And we record this information into the attributes of the node that was basically the previous action. So by doing this, what we end up, if we observe long enough, is that we record the effect of each action on the network. And this basically solves the challenge that I was mentioning before about the autoencoder that breaks the input to output link, because now we are not going back from a given action to understand the relevance of the input. But what we do, given the dynamic of the RLA, we basically look into the effect of a certain action. And also solves the challenge number 2, because now we don't work anymore with a system that has memory. in the sense that we just record the effect of the future. So we split, and anytime there is an agent that relies on past information, then with this system, we can actually work with it. And let me just give you a very quick example for 3 time steps. Basically, you can see that the action that is being taken for each slice, basically there is a component that is physical resource block allocation. Those numbers sum up to 50. That basically tells you that this is a base station that works at 10 megahertz channel bandwidth. And then we have a scheduling policy per slice. And the scheduling policy basically are numbers, but basically are policies like proportional first scheduler, water filling, round robin. And each number denotes 1. So basically at time step T0, what we do, we record the action. And we look for each of the slices. And now here you just see SLS 0, 1, and 2, but reads EMBB, MTC, and URLC that I was mentioning before. So we record for 2 users the information about transmission bitrate, transmitted packets, and buffer size. That was basically is the state of the network that is actually being recorded after the action was taken. So at T0 plus delta. Now, at T0 plus delta, this is the state for the subsequent action that is taken at T1. And at T1, therefore, we basically have a different action and we move. So we have to record this action. We repeat the step. So basically, we end up recording what happens at T1 plus delta. That is the next state. We record again this information, and then we have the subsequent action that coincidentally goes back to the first one. So at that point in time, at T2 plus delta, we record this additional information. So if an action is new, basically creates a new node in the graph. If an action was already present in the graph, we are going to basically record the information. We do this for an observation window. As the longer the observation window, the better you characterize the agent. The shorter the observation window, the less information you will have to characterize the agent. Now, that's an example of a graph, and this is going towards solving the third challenge that I was mentioning before. That is basically understanding the individual impact of each mode of the action, because we are taking both physical resource allocation and scheduling policy. So which one provides what? Here, if we can analyze it well, basically there are different classes of actions. Actions that basically are self, because it's a node that goes into itself. There are actions that basically goes, but keeping the same physical resource block allocation, just changing the scheduling policy in a given slice. There are actions that are on the other way around, keeping the physical resource block allocation, but changing the scheduling. And then there are distinct actions, where basically everything is changing. And now, basically, before going into the results, we did actually implement this into ORAN framework. ORAN basically is now becoming very popular in the way it disentangle the problem of having monolithic solution for the RAN, and basically creates open frameworks to perform, for example, AI via the fact of having XApps that are basically software that actually provides and is capable to configure and parameters that are actually used directly by base stations. So we implemented it as an XApp. And as an XApp, we have implemented into this near real-time rig that is basically this engine taking actions. So from the network, we actually read this state that basically is, like I was mentioning before, buffer size for each user, transmission bitrate, number of packets. This basically goes into a repository, and this repository is actually accessed both by the agent that is an XApp on its own, and by the EXPLORA framework. And now the EXPLORA framework not only reads and tries to understand the agent behavior, but then later also tries to improve the actual agent behavior thanks to the explanation. So before going there, I want to show you the type of explanation that you can build with EXPLORA. Basically, now the point is we have this graph, and what we can do is study transitions. So if we study a transition between two nodes, basically translates into understanding how the agent takes subsequent actions. And given that we have attributes, what we can study is basically comparing the distribution that we have in each attribute. And basically we can get like information that is easy to understand from the network perspective. And here is an example. This is very flexible. So basically you can build such type of explanations per slice and per different elements in the state. Here, basically, I just represent two, the transmission bit rate versus the buffer size occupancy. Also, this allows you to have a very neat structure, because what you have basically is on the one side, information that compares this distribution, and on the other side, the class of the action transition. So this allows you to create a very nice decision tree that basically provides you the explanation. Here, for example, we can see that the agent that tries to maximize throughput for the slice of EMBB basically uses the same scheduling to reduce the network throughput. And with respect to the explanation that we're providing by SHAP, this is easier to understand by a network expert. And now the last point is basically how we can refine the decision that the agent takes, and for example, use it for intents. And one intent can be, for example, improve user throughput. So for this, let me go back 1 second here, and maybe better here. So recall that basically we have an agent that takes such actions, and this action produces an effect on the network state. So before this action are actually enforced, we have all the information, because as I was mentioning before, the way we compute the reward is a very well-known function. So we can compute an expected reward. And when we compute this expected reward, now that we have such a graph, we can look if there are other actions that maybe can lead to a higher expected reward. Now, given that the reward was computed in a way A plus B minus C, not always the highest reward is the best. And we can basically use this information to define a way that if we want to improve the reward, we can look for a different action. Another way to perform basically action steering is instead of looking to the reward, because we have it, we look basically into the expected throughput that the network can get, given the statistic in the past. And we basically found that this is it's possible to define policies that basically end up improving throughput at basically zero cost. So to finalize, we create EXPLORA, that is a framework that creates a network explanation that are easy to interpret for deep reinforcement learning agents. We show that this explanation can also be used to basically refine the agent decision, and this leads to, for example, an improvement of network performance. And all our code is basically public, so you can take it and use it. And that's basically conclude my talk. Thanks a lot.
Thank you. So, any questions? Do you have any questions? I do have a question for you. So the graph, actually attributed graph shows actually the number of the node or the graph node depends on the kind of that configuration values, right? But you know this space is huge. So my question will, do you have actually the like a state exposure problem with your attributed graph?
Yeah, that's a very good question. Thanks. So actually, we found that the agents we look at, they differ very much because of basically the way they've been trained and the purpose they've been trained. For example, the agent that basically aims at providing high throughput uses a very low number of actions. So that's basically remains constrained. So you don't have the state space explosion. Mm-hmm. And also, we found that on the other way around, the agent that instead tries to minimize the latency for the slice of URLC, that yes, uses a larger number of actions, but the state does not explode because of the way the agent was defined at the very beginning. So that agent basically doesn't look for all the possible combination of physical resource block, allocation, and scheduling policy. Basically was defined with a strict number. And in previous work from the Northeastern team, they showed that with that restrict number of actions, the agent was able to perform pretty well. So that's basically why at the end of the day, you don't have the graph explosion because of the number of actions directly. Instead, you could have like a large distribution in storing the action, in storing basically the attributes in each of the nodes, but that basically you can tune it with the window of observation. So if you observe long enough but not forever, basically you end up having a manageable size. It's not exactly.
Listen to speaker again. Oh, okay.
No, it's okay. Right.
Okay. Yeah.
It's my bad.
Okay. Yeah. Yeah. Nice work. And I've just two questions on this. One is, what is the volume of data that is transferred from the RAN to the RIC? Like, what is the volumes that we are looking at? And the second is, how did you quantify the explainability of your system in that sense? Like, how did you say that this is a useful explanation?
Thanks. These are very, very nice questions. Sure. So just to give you a very, very light overview. So we did not look into specific metrics like faithfulness of plausibility of the explanations yet, because the objective was basically to be able to define metrics that were interpretable, for example, by routines. So we want to understand how much we improve transmission bitrate or we reduce buffer size. So that was the goal. And the other question about the specific amount of volume of data in the RIC, imagine that this is basically very, very little information that are KPIs that are monitored over windows of, for example, 100 milliseconds. And basically you have this information per user, but that's not a huge amount of information that is basically streamed to the RAN.
Okay.
Thank you.
Yeah, thank you.
Thanks for the introduction. So I will present our work, change point detection in WLANs with random access point forests. So done here with my co-authors. And first, I would like to give more the context of this work. So next slide. So the context is a management of WLANs, where in an operational situation, administrators need to manage a large pool of WLANs that are at different and possibly distant locations. So you can show below some pictorial representations of a subset of locations from satellite view here, where we expect that each WLAN contains a few tens of access points represented as gray dots. So while managing this large set of WLANs, chances are that these sites are subject to rare unexpected physical modification after deployments, such as obstacles that may necessitate an operational response, for instance, to prioritize on-site intervention. And as opposed to short-term anomalies, here those modifications are linked to changes in the wireless signals that we would like to identify using change point detection techniques. So to detect such modifications, we need to carefully first select the input telemetry And the choice of the telemetry is driven by two aspects. So first, we would like that it correlates with the physical changes in the environment, while we also need that it should not correlate strongly with the user itself. So for that reason, we selected as an indicator the path loss expressed in decibel among the access point pairs of a network over time. And what does it mean? You have some representation here. So below is actually the real data. Here it's a pictorial representation. And given each pair, we can have the series over time, possibly with missing values, possibly with some anomalies coming in about this path loss over time. And here, just three examples of them from the real data. So now I also would like to get more the practical use case of this work with a possible operational setting at a high level. And before we will dive in the actual content and the advance we made in the work. So we are in the situation with a lot of different locations. And here for each location, we can proceed. So it's a possible use case. Possible operational setting where we proceed in two steps here. First, we collect from access points, possibly from an access controller, time sliding windows collection of access points pair of the path loss series. So it may be just 1 week of collected data. And then we use our methodology that it's called random access point forest to detect and aggregate changes over all those series, and we count the detected change here. And after, how to use this? So we perform this for all the locations, and then it gives us some insight about how to prioritize and also raise some alarms in case of detected change point. So in this case, we could prioritize intervention in this location 1. It also gives additional information, so we can have an information about the date of change. Also, can also give spatial information about around which AP to look at, and also can give kind of explainability, so not exactly explainability, but it can give idea about the strengths of the impact on the path loss, with possibly some visual representation, as we will show later, since it's based on decision tree. We'll see in the core of the methodology. So for the rest of the talk, I would like to discuss about the collection campaign. And before we will move to explain the core methodology, so how to detect change points from the actual series. At the third step, we'll also want to focus on discuss how to explore the spatial correlation of those series to reduce the telemetry cost. And at the end, we also discuss the limitations and the future work for this paper. So regarding the collection campaign, we perform a measurement campaign to gather reliable ground truth in a controlled fashion. And to give more details, the collection has been done on a real 5 GHz band WLAN from production with thousands of daily users, where the telemetry has been collected over 2 months, over 33 access points pairs, and the data has been aggregated every 15 minutes. And at the end, we got a total of 2.2 million samples. So additionally, we gathered a ground truth concerning non-relevant events altering the signals. And below here, we can show a temporal view. So that shows the superposition of all the path loss series with some transparency to show all of them with the added ground truth events here. And on the right here, it's a spatial view, which is here over time, the average path loss between each access points pairs. So the artifact is available online if you're interested. And here we can recover the 3 previous series that we showed before that are related to close. So here medium, and long distance between the access points. So now I would like now to discuss the core methodology of the method. So which is how do we proceed to detect the change point on the series. And first, so it's in 2 steps, and now I will focus on the local stage, which is how to summarize a single time series with a single random tree. And in this stage, we proceed in 3 steps. So I have the pointer here. So what we do is first, we generate a random proxy series from the original series of interest. So given 1 pair, each is this specific pair, we got a series, and we will create this random generated series. So how we proceed? So we produce each data point in gray by randomly sampling the original series axis per axis among the position of the orange series here. So we do this for each data point to have at the end sample size which is the same as the original series, and we consider this as a proxy series. And now we create a proxy supervision classification task by associating 0 to this to those elements, so to each sample which is here in gray, and we associate 1 to each sample which is here from the original series. So we put them together, and we put it into a classic, can be a classic tree engine. So for this work, we selected CART engine, but so it does not need to be a complex machine learning algorithm here. And by applying it, it solves a classification task. And what it's doing, a tree, it will partition the space in 2 at each step, which in this case will cut the space in 2, so it will give those rectangles. And from here, we extract rectangles. And those rectangles are just here when the leaf of the tree is equal to 1. So when the leaf of the tree is 1, we keep it, and we keep those rectangles. So here at this stage, we give some weak learner that from each series, original series, give a simple representation of this series. And the second step is a spatial stage. So we have a lot of access point pairs, and what we do here is to aggregate multiple trees in an ensemble. So there is 2 steps here too. So we have the aggregation, which is to just apply this local stage that we just showed before, series by series. And then what we do is to extract the boundaries of all time axis rectangles, that is the elements here over time. So in practice, we can show this what we did step by step. So there is this aggregation stage. So first we took this first rectangle here in blue. We get those rectangles from which we extract the boundaries. So here there is 1, 2, and 3. So we give a count of 1. So it's the detected changes. So we have here 3 detected changes. We can continue with the second one, which will give 3 additional changes. And we continue with the third one, and possibly with all the access point pairs that give those rectangles and those counts. So here we simply took the axis, the time axis of those rectangles to derive those counts. And what we observe is that there is already here clear visible peaks. And if we look compared to the ground truth values that we collected, it quite well aligned with them, with sometimes very clear peaks and sometimes teeny peaks, but it's still quite aligned with the ground truth values. So we wanted to assess the performance of the methodology. And for this, we did an extensive comparison against the state-of-the-art change point detection methodology. And here on this plot, you can show the comparison against a different class of automatic change point detection algorithms. So the name I hear, there are more detail in the paper if you're interested. And at each time, we proceed the same, and we count the number of detected changes observed. And in blue, the blue circles correspond to the top 9 detected changes here, while our ground truth changes are shown in red. And the algorithm with visible peaks yields to better results. So this is not just visually, but we also assess with a quantitative measure. Here it's precision recall area under curve. And the detection of RAP, as we see, match with the ground truth, while other approaches show an increasing presence of noises. And interestingly, this additional noise captures the seasonality of the series. So it may be the weekends, it may be also the holidays that are considered here as false positive change points. So now, detailed results and also ablation study among the few hyperparameters are available in the paper. Now, I also would like to comment how we can exploit the spatial correlation to reduce the telemetry cost. And here, the telemetry cost may be important for the access controller. If we remember what we collect the pair of access points. And this number, actually, it scales in square because there is more and more pairs as a function of the number of access points. But we also, if we remember before, there is also this strong correlation between closed access points. So here we were wondering whether we can exploit the intrinsic correlation among those access point signals. And the answer is yes. So here, just to recall, there is a certain percentage of selected signal that we can collect. And PRIUC, when we take all of them is 1, it means that the 9 over the 9 ground truth events has been detected. And so the most simple way to proceed is just to select a pair totally at random. And if we do this, we get already quite good results with some degradation in the PRIUC, but which is not that strong. And another strategy that we tested is to select deterministically based on the stronger signal, so the ones that are closer here to the diagonal. And if we perform like this, we observe that we can reduce the amount of telemetry by a factor of 3, so which is this line here, without performance loss. So we get still a good results here in terms of PRIUC. We also tested a third strategy, which is selecting the signals at random proportionally to their strengths. But we did actually, we thought it would be a better way to perform, to get better results, but it didn't show good result, not as good as the strong signal strategy. So to conclude, we propose a lightweight ensemble technique for distributed detection of changes. We explored the spatial correlation of the signal to reduce the telemetry cost, and the data artifacts are freely available here, or you can find them in the article. And as future work, we would like to compare on larger data sets. So it was already difficult to get the data set, but it will be interesting to compare on larger ones and also more various ones. And another interesting direction is it will be to study the theoretical aspects of this strategy to take this proxy generation series followed by a random forest strategy. And another way of future work is actually something ongoing, which is a prototype implementation and the practical system aspects and difficulties that are incoming. Thank you. So if you have any question.
Yeah.
Thanks, thanks much. Very interesting. Huet, I'm curious at, you have in your graphs these nice peaks that stand out pretty clearly for the changes. How subtle can they be in order to be still sufficiently well recognized and still motivate or then introduce a change to do some adaptation?
Yes, so in terms of if it is
Yes.
difficult problem and how it is difficult.
So if you wouldn't put up a concrete wall or a metal shield or something, but you would just have a bunch of people standing or redistributing themselves. So the meta question is, how much dynamism can you add to this in the end, and how subtle can the changes be so that you can actually readapt your access point configurations?
Yes, so actually in the ground truth event, there is one which is more difficult to be detected by the others, and in which most of the other algorithms are not able to detect, but we are able to detect. And actually it's the one what we put here, so what we explore in just in 1 week window. And the fact here, it is difficult to detect because of the large number of access points and possible location and possible pairs that we may be able to consider. So this is what makes the problem difficult. Is it that there is a large number of pairs, and if we apply just a single strategy on it, we may not find it, even if an operator will look at it, he may observe it. And in this example, there is just actually only this access point which is impacted, only this location, while the other part of the location are completely normal. So it's more difficult to detect it because there is a lot of kind of noise, which is not very interesting here. But at the end, if we know that this access point is the one that we need to look at, when we visualize, it's kind of clear that there is something happening here, and there is a quick increase in the path loss. So actually, it's more difficult because of this spatial component that makes it difficult to know where to focus and where to really know where is a change point of interest.
Okay, thank you.
Can you hear me? Okay. Thanks about the presentation. I have this question. Basically, you use the intra access point channel quality, okay, to understand if something strange happens to the access capacity of each access point. So my question is, why is it better than considering directly the access capacity to each access point? So do you consider any wireless distribution systems and like that, or what have I missed? So
I didn't get the question exactly.
no, the question was, you use the intra access point channel quality to understand if something strange happens to the access capacity of your network. So my question is, why you use these intra access point measurements instead of the specific capacity measurements on the access point?
Here we are interested in the environmental changes, so more than the impact on the specific access point themselves. So here the interest of taking pairs is that it gives some information about the environment that it passed through. So
okay, so you use use the access point, the kind of wireless connection to see if something strange happened between access points.
Yeah, we can also make some inference about where is the location, where the problem came from. That may not be specifically on this. So actually, we don't want really to consider specific access point issues, and this is like something that we want to remove from this detection, because at the end, what we are interested in is just as those obstacles that are not related to a degradation of the network caused by the network itself, but because of the obstacles or other problem.
But do you want to localize the point, the obstacle, or not? Because my point is that usually we have much more users than access points, no? So it's better to rely on them because you have more information and they are more better distributed than the access point. That's why I was asking.
Yeah, then if we look at the users themselves, it may be that they are not always there. So there are also temporal components to take into account. They may also more tricky to collect this data because then it becomes more sensitive to collect them. So there is some aspect that make that to just stay at this access point pairs makes the methodology easier and easier to collect the data and to process the data and to make all the process work.
Okay,
So,
thank you. Thank you.
Thank the speaker again. Yes, Alex. Thank you. Could you go to here? Okay, good.
Sure. Hello, everyone. It's glad to be here and share with you our work regarding Bluetooth backscatter. I'm Jiang from USDC, and this is a joint work with my supervisor, Wei Gong. So, building a world where everything is connected has been a promising goal in the future. So in this network, these devices unavoidably need to talk to each other, especially through wireless communication. So there are many IoT devices today, and also there are many types to classify them. So in terms of the working scenarios, they can be classified in working in home, factory, medical, and considering their communication distance, IoT devices range can be from kilometers to centimeters. So regarding the power supplement, we have devices that such as need to plug into the wide power line, or they are equipped with batteries. Despite the tremendous IoT devices, they still suffer from some limitations. So for example, in terms of the power supplement, so one kind of these IoT devices, they need plug into the wide power. So this kind setup has poor mobility. So for devices that need batteries, so their working life is limited to 1 or 2 years. And after their battery are run out, you have to change them. And in some scenarios, the devices are hard to fetch, and this takes labor work. So the reason is why this device need to plug into wide line or need batteries is that those IoT devices are mainly based on the active communication, so which consumes large energy. So let's have a brief background of the active communication. So before transmission, the data is mixed with an excitation. So this internal excitation is power hungry. So therefore, backscatter technology shifts the excitation to outside. It reflects the ambient signal and modulates data on it. So since it doesn't need to generate power-hungry excitations, it saves a lot of energy. So this enables a battery-free design with energy harvesting technique. So we have said, so backscatter relies on the excitations. So to avoid the extra deployment of these dedicated excitations, so researchers have been exploring on using Wi-Fi, Bluetooth, LTE, etc. as excitations, because these wireless signals are pervasive and easy to get. So in the past decade, researchers have been have made great progress on utilizing these ambient signals. So like Wi-Fi backscatter, hitchhike, CAB, freerider, etc. However, in this state-of-the-art works, the excitations are all single frequency. In real world, the ambient excitations are all multi-frequency, especially Bluetooth signal. So next, we are going to answer 2 questions. So is multi-frequency ubiquitous? And what problems will there be if it is not considered? So let's look at the first one. So we start this with an example of Bluetooth AirPods in our daily life. So when we open the AirPods, it will broadcast a message on advertisement channels and tell the iPhone that I'm online. So the iPhone will connect to the headset when it receives this advertisement message and connect to it. So after the connection is established, so the audio can be streamed to the AirPods, and the AirPods can also send commands to iPhone. So these data interactions are now switching to the data channels. So let's see more details on this. So as shown in the figure, so we can the iPhone and the AirPods communicate, and they keep switching data channels during transmission. So this hopping mechanism leads to the multi-frequency feature of Bluetooth. Here is a statistical result of channel transmissions. So the bar indicates the transmission times of each channel, and we can see that the cell phone transmits on almost all the channels, and its transmission is focused on the left, right, and the middle band. So we know that Bluetooth is hopping on different channels. The question is, do all devices have the same hopping pattern? So the answer is no. So hopping pattern is also diverse among different devices. So as shown in the first and second channel of this particular case, we can see that devices have different transmission preference. So this Xiaomi device allocate more transmission on the second channel, while the Huawei device allocate more transmission on the second channel. And while the laptop does not use the second channel. So since Bluetooth hopping is adaptive to environment, the channel distribution of different devices are diverse. So now we get that multi-frequency is ubiquitous. So what problems will there be if it is not considered? So we take a measurement of prior BOE systems, RBOE and FreeRider, on the multi-frequency excitations. So when the number of excitation frequencies increases from 1 to 8, so the output suffers from 88 decrease. So why FreeRider and RBOE fail in multi-frequency excitation? So now we have a multi-frequency excitation like this. So the white box denotes this hopping excitation. So to communicate with standard Bluetooth, the target channel should also be hopping. So here is a target hopping sequence. But the problem is that the FreeRider and RBOE treat the multi-frequency as single frequency. So the backscatter signal is diverse, but they do not match the target channels. So if the backscatter packet is not in the target channel, so this transmission would be invalid. So therefore, the prior systems suffer from a low ambient utilization, and the utilization is 33%. So in this case. So we propose Dan Blue, the first system. So it backscatters in a standard Bluetooth hopping way. So the basic idea is that first, our tag takes any frequency Bluetooth excitations. So then the tag backscatters it to another any frequency Bluetooth channels. So in this way, the tag would establish a connection with the simple smartphone because its target channel is hopping with the standard device. So in this work, we made two main contributions. So first, we introduced a low latency frequency identification scheme. And second, we proposed a wideband channel hopping. So that is compatible with the standard device. So to achieve this goal, the first challenge is how to identify excitation frequency. The most direct way to identify frequency is to decode the packet like active communication, but the decoding circuit is power hungry because the decoding process is an inverse of the transmission. They both need the excitations to downgrade the carrier signal. So this is a power hungry operation, and it is not supported on our ultra low power backscatter tag. So Another work, Cyan, proposed a passive bulky acoustic wave filter to transform the FSK signal into ASK signal. So the tag can extract the envelope using a simple rectifier. But however, this the bandwidth of this BAW filter, it cannot cover the Bluetooth channels. So we introduce an assistant edge to do frequency identification. So the basic idea is our edge identifies the ambient frequency and it forwards to the tag using ASK signal. So the multi-frequency is diverse, but its hopping pattern is determined by the selection algorithm, which is specified by the BOE specification. So to accurately identify the frequency, so the edge adopts a BOE module to sniff the input of this selection algorithm and forwards them to the backscatter tag through ASK signal. So this mechanism is simple and accurate, and also the ASK downlink, it puts little computing burden on the tag. But we should, but it seems everything is fine. But the key is to ensure the whole process is low latency and the edge is low cost. So because the ambient hopping interval can be the minimum hopping interval can be 7.5 milliseconds. So our edge must forward the frequency information within this interval. So we propose a low latency design. So it integrates a commercial off-the-shelf chips. So to reduce the forward delay on edge, we adopt high-speed SPI interfaces and UARTs between chips, and the downlink packet encodes data in symbol level instead of packet level. So the total delay is less than 7 milliseconds, which is smaller than the minimum hopping interval in BOE. So by using these COTS chips, the cost of our edge is just $24, which is much smaller than the USRP. So now we have given knowing excitation frequency. So how to backscatter it to another dynamic channel? So our goal is to backscatter dynamic excitations to dynamic channel. So each excitation and target channel pair needs a clock. Therefore, the total clock selection complexity is O(n) squared. So prior system RBOE treats the multi-frequency excitation as single frequency. So to backscatter to each target channel, RBOE needs to get 1/7 fixed clock resources. So the RBOE can only support 7 channels. It cannot cover the 40 Bluetooth channels. Different from RBOE's fixed clock. So DynBlue adopts a programmable clock. So for different backscatter channels, the clock can be programmed to dynamic states while maintaining a 1/7 clock resources consumption. So thanks to the dynamic reconfiguration, so DynBlue can cover all the 40 channels with just 1/7 resources. So to enable fast clock switching between these clock states, we store this clock state in a hash table. So the clock selection complexity can be reduced from O(n) squared to O(1). So now we put it all together. So we have a multi-frequency excitation. It hops on the dynamic channels. So our edge assists the tag to identify this excitation frequency. So the tag receives these commands from edge and it reconfigures the clock for each excitation packet and is able to establish data connection so with a standard receiver. So the key is that the tag can identify the multi-carrier, so it can backscatter the excitation to any dynamic channel that matches the standard receiver. And meanwhile, our low latency edge supports standard hopping interval. So it will not cause delays in the backscatter transmission. So we have built many prototypes, including edge prototype, verification tag prototype, ultra low power tag prototype, and IC simulation prototype. So compared to verification prototype, over 10 times power reduction is realized in the ultra low power prototype. So the total power consumption of the IC is around 800 microwatts, which is less than 1% of the verification prototype. So in end-to-end experiments, DanBlue maintains an excitation utilization rate of 97% and a good put of 28 kbps on the different frequency diversity. And it has a maximum uplink distance of 25 meters. So behind these high utilization rates in end-to-end results, DanBlue's excellent identification capability plays a vital role. Our edge-assisted identification delivers an identification rate of more than 95%. Meanwhile, the average BER of the different target channel is below 0.1%. So last is a connection application. So we show that our DanBlue tag can build a connection with standard BLE receiver and transmit data. So these excitations and edge are not shown in this slide. So first, DanBlue tag it sends a connection request packet to the BLE receiver. So the terminal in the right shows the status of the receiver. So when the receiver it receives the packet from the tag, it prints connected when it is connected. So the tag then sends a write command with content of a message from DanBlue tag. So the receiver in this connection it displays the accepted message. And at last tag, this tag terminates this connection, and the receiver reports that the connection is disconnected. So there are also some limitations of our work. For example, the tag can only handle single excitation source currently, and we also have some limitation on the downlink range, and also some limit concurrency. So final conclusion. So we have presented DanBlue, a BLE backscatter system that works in a standard Bluetooth hopping way, and it supports hopping from any excitation to any target, and it can seamlessly build connectivity with active radios. Okay, thank you.
Okay, thank you. Any questions? Let me ask the first one.
Okay.
So I think the key here, the key problem is because we have multiple frequencies and you're doing the frequency hopping,
Yeah.
right? And the Bluetooth looks like it's a pretty good example under the here, but I do have two technical questions. Number one is, so do you think that this Bluetooth frequency hopping algorithm or this kind of thing is kind of fixed for all the one, or can we have customized or dynamically change, our frequency hopping, blah, 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 all this one?
Okay, so this frequency hopping, it is determined by the BLE specification. So there are two hopping algorithms, which is also it is specified by the specification.
Okay, so it's a standard one.
Right. It's a standard thing. Yeah. Yes.
Okay. Then number two question here is, I think this one can be applied not only in Bluetooth, right? So this likely can be used as other wireless technology because it's very common for other technology also use multiple frequency.
Yeah.
So what's your future work for the other?
Actually, we did do an experiment on the Wi-Fi. So we have tried on one Wi-Fi, single Wi-Fi excitation, but we tried to backsell it to multiple Wi-Fi channels, and I think this frequency identification scheme and wideband hopping, it is compatible with different wireless signals. Yeah.
It could be more complicated for other wireless because
Yeah,
Bluetooth
yeah,
it could be simple,
yeah.
right? Any other questions? If no, then let's think the more round. And this is our last technical talk today. Okay, thank you.
Okay, thank you.